Hello, I'm Zhenghao Sun, a PhD student from City University of Hong Kong. The title of our paper is Complexity Configurable Learning-Based Genome Compression. In this paper, we conduct exploration research on how to improve the compression efficiency with learning-based genome compression. The volume of genome data grows rapidly as the cost of sequencing a complete genome becomes much cheaper than decades ago. Since the genome data requires high fidelity, lossless compression is normally used for compressing such data. Here is an example of complete genome of Homo sapien mitochondria. Specific design codecs are more efficient than general codecs for compressing such genome data. In recent papers, learning-based genome compression shows high compression ratio over such genome data. However, such performance improvement is achieved at the expense of high computational complexity. In this paper, we propose a complexity configurable learning-based genome codec to achieve a good balance between coding complexity and performance in lossless genome. Here is the overall architecture of proposed encoder. In our design, the original sequences is partitioned into group of bases. Each group enjoys its own initial context and has a learning-based inference part, which are encoded in different methods. The arithmetic encoding is finally applied to compress the bases. Together with the parameters, the bit streams are saved to file. After receiving the compressed file, the decoding side firstly passes the parameters, then partition the binding strings into the same number of groups as the encoded side. Each group is processed individually. With the support of the same model, the arithmetic decoder is able to reconstruct the original basis from the binary strings. For the learning-based inference part, we applied a classification neural network for probability estimation. The network takes context as input and estimates the probability of current symbol. Specifically, it consists of one-dimension convolution layer for local feature, LSTM layer for long-term feature, and a multi-layer perceptron for classification. The network finally outputs the probability of each symbols based on the input context. Since the probability of each symbols in the initial context part is still unknown before we apply the learning-based estimator, we apply the low-order Markov model to do such inference. On the left is an example of two-order Markov model with two symbols. The previous two symbols is treated as previous state. The second character in the next state represents the current symbol to be encoded. With this Markov chain, we can form a transition matrix by statistic method. The experiment shows the compression ratio is higher after introducing Markov model to initialize the probability in the context. We test the model over 100 human mitochondria, which consists of more than 1.6 million bases in total. Compared with deep DNA, our model is able to configure the complexity, making trade-offs between compression time and compression ratio. Here are some reference works for this. This work is supported in part by the National Nature Science Foundation of China and in part by the Hong Kong ITF. If you have any questions, feel free to contact me.